All right. All right. Welcome, scholars. Are there any questions? Do you guys have any questions about anything before we kind of get into it? So, I want to hope everyone had a great weekend. We're kind of in the home stretch as far as the new material. So, chapter 4 will be the culmination or the end of everything. I think we did section 4.1 last time, which was an introduction to the integral. And so, the integral is basically the reverse of the derivative, right? So, for these first 3 chapters, we were exploring what do we mean by the derivative, essentially the slope of the tangent line at a point, and ways to find it. We introduced it, ways to find it, some applications, things of that nature. And then, so again, last time we started with the derivative and we started exploring ways to work backwards to get back to the original function, all right? Okay, so we're going to continue that narrative today. Grab this. Ooh, good job. Okay. And I'll minimize that for now. Okay. So again, we're going to continue chapter 4 on integration. And today we're going to be looking at section 4.2, antiderivatives as areas. Again, I'll be kind of lax. I'll be lax with the attendance for right now. I mean, as far as people showing up late, but again, this doesn't really pertain to anybody here right now. I'm just saying, just for the sake of saying. But if I do notice people coming in like after 15 minutes, then I'll start to lock out the class. And then you don't want to be caught on one of those days where I lock out at 15-minute mark, because then it'll count as an unexcused absence. We don't have that many sessions remaining, but again, you don't want to jeopardize your money. You paid money to be here. You come this far. You didn't come this far to come this. You didn't come this far to just come this far. You came this far to go all the way, right? It's pretty much right there for the taking. I mean, again, this is like non-proctored, non-proctored environment, unlimited attempts. I mean, it don't get no much better than that, right? You got help. I'm here. Pearson explains everything. You can kind of work the system, and it'll be okay. The intent behind the design here is really just to expose these concepts to you all and try to encourage you all to try to learn as much as you can. It's not really like you're not in like a classroom where all you have is paper and pencil and a calculator. So you have a little bit of wiggle room. So just do your best to be on your P's and Q's, milk it, do what you need to do and keep it moving, right? Okay. There we go. That was a little bit better. Okay, so antiderivatives is area, right? So again, we introduced the antiderivative or the integral, which is basically the reverse of the derivative. And so now we're going to explore like, I wouldn't call this necessarily, I mean, I guess you could call it an application, but like, what does the antiderivative tell us in the terms of area? So let's look at it. So a few objectives here. 1, find the area under a graph and use it to solve real world problems. I guess it would be an application. 2, use rectangles to approximate the area under a graph. Okay. So let's see. We have a vehicle travels at 50 miles per hour for 2 hours. How far has the vehicle traveled? Now, obviously you can do like, just unit arithmetic, right? 50 miles per hour times 2 hours is what, 100 miles, right? So if we did an xy on the x-axis, we had time versus the velocity. 2 hours at 50 miles per hour. And so I just want you to kind of see this, right? Where is it? So notice we have time down here. They went for 2 hours and they went for a speed of 50 miles per hour. So then the area of a rectangle was what? The length times the width is what? In this case, it's going to be 100 miles. All right. So they traveled at a constant speed, which was that flat horizontal line kind of at the top. And then we want to think about the area under that curve. And notice the area under the curve is 100 miles, right? So I just kind of want to dive into the way the book explained it. So if it travels at 50 miles per hour for 2 hours, how far has it traveled? The answer is 100 miles. I feel like it's not too terrible to generate that number. We treat the vehicle's velocity as a function. So we're looking at the velocity function, right? And it's a constant. It's just going a constant 50 miles per hour. We graph this function and sketch a vertical line at x equals 2, and we're basically observing the area under the curve, or the line in this case. The rectangle measures 2 units horizontally and 50 units vertically. So the area is the distance the vehicle has traveled, which is 100 miles. Okay. So the image kind of gave it away, but let's keep going. So it says the velocity of a moving object is given by this function, where x is in hours and v is in miles per hour. Okay. Use geometry to find the area under the graph, which is the distance the object has traveled, or which is the distance the object has traveled. During the first 3 hours, and then between the 3rd hour and the 5th hour. Okay. Kind of need some graph paper. I don't want to take too much time. I might piggyback off. I'll do a rough sketch, just in the interest of time. And I'm going to piggyback off of my prepared notes. Let me see. So if we're doing similar to the previous one, right, where we have a velocity function, and the function here is 3x. So if we graph y equals 3x, say this is our positive x in this direction. Again, this is just going to be a rough sketch. Positive y in this direction. All right. Okay. Y equals 3x. Let's go. I guess we can go. I don't know. This is just again a rough sketch. I'm not drawing it to scale, but something along those lines. All right. Y equals 3x, a positive slope, and then it says to use geometry to find the area under the graph, which is going to be the distance traveled. So the x-axis is in hours. All right. So the unit there are hours. So we need 5, right? So let me see. 1, 2, 3, 4, 5. So when that's a 1, this right here should be like 3. So then that should be 6 right here. What, 9? Basically going by 3s. I know it kind of goes off. And then like 12, and then 15. Okay. I'm just gonna kind of work with that. Again, this is like 1, 2, 3, 4, 5. And then what is that? Our velocity. This is our velocity over here. Hang tight, hang tight. Like this, like this. And I want to rotate it and shrink it down a little bit. Velocity. Okay. And so, I mean, I kind of did the scale. I tried to line up the y values approximately where they should be. So it says, let me see. So if we want the area under the curve from 0 to 3, the first 3 hours, right? So I guess we can use this color. Matter of fact, I'll change this. So if I see it right there, the first 3 hours. So from 0 to 3 is basically from here to here. I can get it to work. Why is it not working? There we go. Ooh. Device is acting up a little bit. Okay. There. So that really is supposed to line up with the 9. Like, again, this is what I meant by it's not drawing the scale. So it would be better if I did this with like graph paper, then the numbers would line up properly. I'm going to just move this a little bit manually. This is really kind of supposed to be more like that. I'll move this one too. Approximately, right? Again, because at 3 times 3, we should be at the 9. So then the area under the curve, right? So area of a triangle, we're going to use geometry, all right? Area of a triangle is what? 1/2 the base times the height. So in this instance, we're going to say what? 1/2. Our base in this case is 3. And our height, I think, is 9 because 3 times 3 is 9. All right. So 27 over 2, 13.5 miles, all right? So 13.5 miles. And again, we just did the area under the curve, area of a triangle. This is 1/2 the base times the height. We have a right triangle. All right. Oh, and let me see style. I meant for this to be kind of like that. Okay. So that's from 0 to 3. We got 13.5 miles in the first 3 hours. And then between the 3rd hour and the 5th hour. So we did from 0 to 3. If we want from the 3rd hour to the 5th hour, right? We can just do the right triangle from 0 to 5 and then subtract our previous answer from this answer, right? Let's see, I'm going to duplicate this, slide it over, and stretch it. So it kind of goes off the chart a bit, but that's okay. I mean, you should be able to conceptualize, continue the graph and all that. Okay, so then from 0 to 5, let's make that one, let's go orange. So then the area of the orange triangle, let me see, it's going to be 1/2. The base in that case is going to be what? 5. The height is going to be what? 15. So 50 plus 25, 75, is that right? Mm-hmm. Half of 75, 35, 36, 37, 37.5. So this one is 37.5 miles. So then if we want the distance, I'll just say something like the distance from 3 to 5. I'm just giving it a label. We would say the 37.5 minus the 13.5. If that were 20, that'd be 17.5, 17, 10. That can't be right. I didn't do that right. What's that difference? 20, 17.5, 24, 23.5. Okay, let's go 23.5. No, 23. What is that? If you add 3, here, let me do this. Hey, Google, what's 37.5 minus 13.5?
37.5 minus 13.5 is 24.
24, okay. That's what I kept feeling. I was like, I think that number's off. 24 miles. Okay. So between the 3rd hour and the 5th hour, we got 24 miles. And for 0 to 3, we got 13.5 miles. Okay, let's see how do we do. 13.5 looks good. And conceptually, the second one should be good to go. Oh, 18. Okay, so they did theirs a little different. Let's see if we get the same result, though. Let me just kind of check. Right there, 24, right? So I think that's what we got. So what we did, again, we're using geometry. We did the larger triangle. We did the area of the larger triangle minus the area of the smaller triangle. What they did, they broke that little region up into its simple shapes, which is basically a rectangle and another right triangle. And so they found the area of each of those two simple shapes, and they got the same thing. An area of 24 miles, or a distance of 24 miles. All right. So 2 different ways of doing the same thing, and we're Gucci. Okay. All right. Quick check. I usually leave for you all. Okay, let's keep going. So Riemann-Simon. So the last two examples, the area function is an antiderivative of the function that generated the graph. Is this always true? Is the formula for the area under the graph of any function the antiderivative of that function? How do we handle curved graphs for which the area formulas may not be known? We investigate the questions using geometry in a procedure called Riemann summation. All right. Okay, let's keep going. So in the following figure, the closed interval AB is divided into 4 subintervals, each having a change in x. That triangle x, we call that delta x. It just means some small change in x, right? So the delta x, or the change in x, is going to be b minus a over 4. So we take the right endpoint minus the left endpoint divided by 4. That gives us 4 subintervals. So what we're using here is this is a technique called Riemann summation. And it's what it is. It kind of serves as like an approximation for finding the area under curves. In the previous 2 examples, we were finding the area under simple shapes that we know how to find the area of, right? The first one, we found the area of under a constant function. So that created a rectangle. We know how to find that area, length times width. And then the second example, the simple shape created like a right triangle. So the area of a right triangle is 1/2 the base times the height. So we know how to find that one as well, right? So now we know how to find the area under those curves as well. So this whole Riemann summation is an approximation for the area under the curve. So say we have some curve figure like was shown in red, and this one, these Riemann subintervals, they line them up based on the top left corner. When we're doing these summations, you have three different choices, and they all give you like the same result. You just need to be consistent. But if you look at the top of each subinterval, the top left corner is what's touching the curve, and so it's based on the top left corner. You could also align each one based on the center of each subinterval, and you can also do it based on the top right corner of each subinterval, right? Okay. Let me see. The height of the rectangles are f of x1, f of x2, f of x3, and f of x4. Right. So then now again, these rectangles serve as an approximation for the area under the curve. So then, but the rectangles, each rectangle, we know how to find the area of each of those individually, right? Now it's not going to be exact, but it'll give us an approximation. Now there's a little bit more to the story, but let's kind of keep going. Okay. So the area of the region under the curve is approximately the sum of the areas of the four rectangles, right? So this little equation here is basically the sum of each, the area of each rectangle, right? The length times the width. So the height, which is f of x1 times the width, which is delta x, plus the next rectangle, the height is f of x2 times the width, which is delta x, right? So we're adding up the area of each of those four rectangles. We can denote this summation. We can denote this sum with some summation or sigma notation, which uses the Greek capital letter sigma or sigma, right? So it's going to be the sum as I goes from 1 to 4 of f of xi times delta x. What's the difference? Okay, it's the same thing, right? This is just two different ways how we might write summation, either where the indices are on the top and bottom of the summation symbol, or the slightly to the right of the summation. These mean the same thing. This is read the sum of the product f of xi times delta x as I goes from 1 to 4. To recover the original expression, we substitute the numbers 1 through 4 successively for I and f of xi delta x, and write plus signs between the results. Okay, that's kind of a mouthful. I really feel like it's much more simple than it sounds, right? At first glance, it can maybe seem a little daunting, but we're gonna work a few examples seeing this in action. And again, it's not as bad as it may sound. Okay, so write the summation notation for this, right? So this example, we're just getting some practice on writing summation notation, right? Okay, so we need an expression. Okay. Anybody notice anything with these numbers, right? If you look at these numbers, what kind of pattern can you notice? So sometimes when we're trying to convert these little series like this into summation, you might start with like considering what position is each number in, right? So for instance, the first position, this is like our first position. This is our second position, our third position, our fourth position, our fifth position. Now how could we, what kind of equation or formula could we come up with that would take us from the blue to what was given, right? What kind of correlation can you make between those blue numbers versus the numbers that were given? Anybody see that going once, going twice, right? Okay. So I think it's what? Double, right? If we say 2 times 1 is 2, 2 times 2 is 4, 2 times 3 is 6, so on and so on and so on. So it looks like with the series that was given is going to be 2 times each of the blue numbers, right? So then we might capture that in the following manner. Okay. So then we'll have what? The sum as I goes from, let me see, 1 to 5 of 2i. All right, let's see if this works, right? So when I is 1, we get 2. When I is 2, we get 4. When I is 3, we get 6. When I is 4, 8, 5, 10. And the summation means add them all up. So again, this would be the summation, or the sum as I goes from 1 to 5 of 2i. Okay. Let me pause for the cause. I feel like there should be questions, but I know how you guys don't like to talk. It's okay. I will say this though: whoever does the most talking does the most learning. The only reason I know this stuff is because I talk about it like all the time, most of the time without thought. So I get kind of excited when it makes me think, right? But yeah, whoever does the most talking does the most learning. essentially. Okay. So note that we're adding consecutive values of 2, right? Okay. So the sum as I goes from 1 to 5 of 2i. Okay. Okay. Quick check I'll leave as an exercise for you all. We are cruising. Let's back up some. Wait a minute. Write the summation notation for this guy. Okay. Okay. So what are we adding up? The only thing that looks like it's changing is that subscript for the x. And it looks like its x is going from 1 to 19. Okay. So then this we might capture as the sum as I goes from 1 to 19, g of xi times delta x. So it looks like we have a total of like 19 subintervals. All right. So again, just more practice on writing summation, how to go from in that expanded series form into summation notation. Okay, I think we got that there. All right, let's look at this one. So now, okay, so we started with like a series where it was expanded out and we converted it into a summation notation. Now we want to try starting with the summation notation and going the other direction. Can we expand it? So given the summation, or express the summation without using summation notation. Okay. So it's the sum as I goes from 1 to 4 of 3 to the power of I. Okay. So when I is 1, we would get 3 to the power of 1. Plus, when I is 2, plus when I is 3, plus when I is 4. And then, now we can go further. We can take it further. They might want us to stop there, but just in case, 9 times 9 is what? 81, 27, 9, and that's a 3, right? So what is that? 90, 110, 117, 120. So they might take the first expression, but they basically should add up to 120. Let's see how do we do. Again, are there any questions? Any questions? Oftentimes in life, if we don't like the outcomes that we're getting, 9 times out of 10, we're not asking the right questions. If we're asking any questions at all, right? So if you're not asking the right questions, how do you expect to get the right answer? Because you'll get the right answer, but if you're not even looking for it, then it'll just pass you by, right? Opportunities don't go away; they go to who's next. So again, just it doesn't hurt to ask questions. That's the whole point of this is to ask questions. That's it. If you don't ask questions, then they'll take you for a ride. How do you expect? That's how we get to the bottom of stuff. Like, is this true? Does this make sense? Is this the best? Are we being tricked or bamboozled? Right? Questions. Okay. All right. Let's see. Quick check. Okay. Express this without using summation notation. Okay, so we don't have any details about the function, but we can still expand it. So then this will be now. Okay, we're not going to write out all 30 terms. We can write out a few, and we do that in the following manner. So we're going to say h of x1 delta x. That's the first one, plus the next one h of x2 delta x. Yeah, that's right. And then the way, instead of writing out all 30, we'll say plus. Ellipses means continue the pattern until you get to the last term, which is going to be h of x30 delta x. So wherever there's an I, we're putting 1, 2, 3, 4. And we use the ellipses to, again, the ellipses just mean continue the pattern. And then you write the last term that says, hey, you continue the pattern until you get to 30, right? So that's how we would write something of this nature. We're not going to write out all 30. We're not going to write out all 30 terms. Okay. All right. Let's keep going. Yeah, I think we got that one. So, okay. All right. So we're kind of moving and grooving. We're actually almost done with this section, I swear. I think what I'll do today is go through some of the corresponding homework instead of going to the next section. I don't know, maybe. I don't know. I'm just eager. Like I keep wanting to go to the next section. I was like, no, let's slow it down a little bit. Because right now we're actually like a day ahead. So this was really originally intended to be Wednesday's lecture, but I was like, it's fine. All right, so consider the graph of this function over the interval from 0 to 600. Approximate the area by dividing the interval into 6 subintervals and then into 12 subintervals. So let me see. All right, this one is a little bit involved. From 0 to 600. So I think we said what? B minus A over 6 would be the number of subintervals. Let me do that really quickly. So then for part A, I'm just going to take some notes here. I'm going to need more space. So if we said B minus A over 6, let me kind of do this. So for the subintervals, if we said B minus A over 6 in this case, that would be 600 minus 0 over 6, which is what? 100 for each sub. So the width of each subinterval is going to be 100 units. Okay. And then just for B, I'll do something similar. So 600 minus 0 over 12. So what? Divide that by 2. Should be 50 units. Okay. So the width, so 0 to 600. Okay. And then we got that parabola we need to graph. All right. Approximate the area by the subintervals. Okay. All right. So let me. I was kind of avoiding doing it by hand. Is that the last one? That essentially. So I'll try to go ahead and do it. Copy. It's a little bit time consuming, but I do kind of want to work through this one. Let's paste. Okay, and then I need some graph paper, like so, like that. Expand. Okay. All right, and then graphing the quadratic. I'm going to take some notes again. What form could I put it in? If I did completing the square, I just want to do completing the square on this guy real quick just to see what it looks like. Let me think. I could use quadratic formula, but I kind of want to do completing the square. B over 2 squared, so let me see something. Let's see, if we have this, negative x squared plus 600x. Okay, so if I did my b over 2, let me factor out a negative 1 first. Okay. I'm going to add 0 in the form of b over 2 squared. So negative 300 divided by 2, or is it negative 600 divided by 2 is negative 300 squared is going to be what? 90,000? I'm going to just write it as plus 300 squared and minus 300 squared. Again, this is just, you don't really need all this. I'm just kind of playing around a little bit. It looks like it's going to factor into something like this. Let's see. Okay. Is it x minus 300 quantity squared plus 4 zeros? Is that right? Let me see. Outer inner will be negative 600 and last plus 900. Yeah, 300 squared. I think this is okay. All right. You don't really need all this. I'm just trying to graph it. We could have also used the vertex formula. Let me just put that just as a recap. Vertex formula, which be the h, which is the x coordinate of the vertex, negative b over 2a. Okay. And I just want to check negative 600. So the x coordinate of the vertex would be at 300, right? And then when I put it in standard form, the coordinates of the vertex are 390,000, so that's fine. Yeah, I think we're good. Okay. Okay. So our x-axis, we're going from 0 to 600. The coordinates of the vertex are 390,000, it looks like. Yeah, right by 300 and up by 90,000. So what needs to be on the y-axis? So maybe 100,000? Oh, and it's upside down? Okay. And we said what? 0 to 600? Okay. And the vertex is at 90. So then we'll probably go to maybe like 700 on the x-axis and 100,000 on the y. Okay. So something like this. So say the origin is about here. Let's go 1, 2, 3, 4, 5, 6, 7. We need to go to like 100 here. We can go 2, 4, 6, 8, 10. That's good, I guess. Say this is the positive x in this direction. Positive y in this direction. Okay. Let me see. So this would be 0. This is like 100, 200, 300, 400, 500, 600, and 700. Okay. And then we said we needed to go to 100,000 on the y. Let me think. So I think this is like, I mean, not, yeah, 100. So this is like 20,000, 30,000. No, sorry, not 20. 40,000, 60,000, 80,000, and then 100,000. We said the vertex was at 390. So the vertex we got was here. 300 right there, it looks like. Okay. Axis of symmetry. Let me see if we go, what if we put in 200 into the original? You know what, I'm gonna just plot my points. I'm gonna use my calculator because we do gotta crunch the numbers and I'm being a little bit lazy. So I'll go here. All right, that's right here. Okay. Reload and refresh. Okay. Come on. There you go. Okay. So then I'll go to my y equals. I'll put my 600x minus x squared. Okay. And I'm going to just go ahead and pull up the table because that's essentially what I was going to do anyway. So I'll go to table set. I want the table to start at 0 and I want the corresponding y's. I want my x's to change by 100. Okay, and I'm gonna just look at the table. Okay, so I think our numbers are good. So now just use this, right? So now when we calculated earlier, we got what, 300, and that was like 90,000. So those are the coordinates at that point. 0, 0. So this started the origin. So we had this point, 0, 0. 100 and then 50. So 150 is going to put us here. So we have that point there, and I'll label it 100, 50,000. I could lose a lot of those extra zeros, but it's fine. 280, so over 200 and up to 80. Put us here. 280. All right, okay, you know that's there. Okay, then we can use the axis of symmetry at that point. All right, so, or the table. 400 should be here. 500 should be here. And then 600, it should be back to 0. Okay. Okay, so we get a curve. We get a curve like this. That's decent, okay. Okay, let's see what else. Approximate the area. Okay, so we got our 6 subintervals, right? We did from 0 to 600. We have this. So now we need to do our Riemann sums. So let's build our Riemann sums like we saw, like we introduced. We're going to use the left endpoint. Notice if we use the left top corner of the rectangle, the first one has an area of 0, right? So I'll do those in orange. So the first one is here, right? The second one, the top is here. I guess we can do like this, or actually. I think we said each rectangle has a width of 100. I'm going to duplicate that. And I'd like to get rid of just a little thing. Come on. Ah, good, it worked. Okay. I'm going to put this here like that and drop this down. All right, okay. So let me see. The next one, if I duplicate, is going to be like this, right there. And this guy's going to stretch up and connect there. If I duplicate, the next one is here, and stretch it up to there. Duplicate, like this. And this one goes to there. Duplicate. This is the last one, like this. So then,
Hey,
okay, I'm going to be
Professor,
a
is
little
it
bit
fine if
fancy here.
I'm
Say
sorry,
that again.
can I leave and join back off my laptop?
Yeah,
Okay,
yeah,
I'm
that's
sorry,
fine.
sir.
You don't have to. Yeah, good, you're good. Let me see. We got a good amount of time. Let's keep going. I'm gonna be a little bit fancy here, just kind of whatever. Let's go here. Okay, this is a little bit extra. Let's go style. That could be thin, fill, I want like that. And I'd like to duplicate that. Come on, duplicate. Okay, duplicate. I'm just adding some color to it just because this is like the fun stuff, right? You get to do a little bit of coloring. Duplicate. I mean, not that the other stuff isn't fun. The other stuff is fun too, once you figure it out. I'm pretty sure it could be torturous, like when you're trying to figure it out. But anyway, so we have our curve, and now we have our Riemann sums based on 6 subintervals from 0 to 600. So again, to get the width of each subinterval, we said b minus a divided by 6 in this case. So we said 600 minus 0 divided by 6 because we wanted 6 subintervals. So that means each subinterval was a width of 100. So then to approximate the area under the curve, we're basically going to add up the area of each of these triangles, each of these rectangles, right? Let me think. Okay, so I'll do each rectangle in orange. So the area of the first rectangle, I'm just going to put it as a 0, right? I'll just say the area. Oh, clean it up right here. So the area is approximately. We're going to say what? The first one is 0 because it has no height. So then the second one, that height is what is that? 50? 50 times 100. So a height of 50 times a width of 100 plus the, oh, sorry, not 50, but 50,000. Let me clean it up. So this is what I mean by like it can be a little bit lengthy. So we got the first one, the second one, the third one goes up to 80,000. So we would say the 80,000 times 100 plus, I think the max we got was 90,000 times 100. And then I think it's kind of a repeat. We could even say 2 times each of those previous ones. And I think for the sake of time and space, let me keep going because you might need to see this. So 80 times 100, 50 times 100, and another 0, right? 1, 2, no, we didn't need that last 0. Because there should be 6 subintervals, right? So let's check real quick. 1, 2, 3, 4, 5, 6. Okay, so then we just crush those numbers, right? Now again, this little experience is like it's similar to how we introduced the derivative, where we did the whole limit as h tends to 0 of the difference quotient, and so to find the derivative, initially it took up a whole page. That's kind of like what this is. This is like an introduction, what we mean by the integral, and we're going to explore some more sophisticated techniques to find this. This is just for introductory purposes, right? The way we're doing it right now. Okay, so then here, what I'd like to do, I'm going to go back to my home screen and just basically add those up. I'll say my 0 plus 50, 1, 2, 3 times 100. Now I'm tempted to just factor out the 100. I'm gonna use a little bit of algebra here. I'm going to say 100 times parentheses. I'm going to say 0 plus. I'll do 2 times 50. 1, 2, 3 plus 2 times 80. 1, 2, 3 plus 90. 1, 2, 3. All right, because we had 2 of the 50,000s, 2 of the 80,000s. The 0 is indifferent because the 0 collapses a lot. And we basically are going to distribute 100 across this summation, right? So then the area that we get is, what is that? 3.5 million. 3,500,000. Nope, 35. I think that's 35 million. We got 6 zeros. 1, 2, 3, 4, 5, 6. 35 million. Okay, so that's for part A, right? So based on those conditions, whatever. Okay, let me clear this out. This one. Oh, come on. You can do it. I believe in you. What if I go like this? Try again. Come on. You know you want to work. Okay, well, let's try this. There we go. Okay. I feel good about this. Okay, so I think the second one asks us to do 12 subintervals. So instead of 6 subintervals, we basically want to repeat this, but with 12 subintervals. So I'm going to try to piggyback off of what I already have. So what I'm going to do is duplicate. I want to duplicate this slide. My device behaves. Duplicate. And then with the second copy, I'm going to try to customize it. I'll leave this as a reference in the corner. I'm just going to leave that as a reference up there. That's from part A. Okay. So then I think I'm going to get rid of these boxes. I'm going to just get rid of all of this. And then try to get that one. I already know it's going to kind of act up. Can I just target that? Yeah, there we go. There we go. Okay, and I'll leave those ordered pairs because I think those are going to be the same. But in part B, again, this is part B. This was part A. In part B, we want 50 subintervals, right? So we got like this one here. I'm just going to kind of highlight them. How could I do it? Here it is. Something like that. Let's see. So, oh, and we had our graph paper. I was doing this thing again. Okay, let's go like this, like this, like this. There we go. Like that. No. There's usually a 1. Let's try 1. I think 1 doesn't. Looks like we're missing some stuff. Where'd it go? Let's undo. Okay, that's what I want. Sorry, my stuff is gonna acting up a little bit. Okay, that's fine. There we go. Okay, let's try this again, like this. What's the time? We're looking good on time. Like that, like this. No, oh, and it moves it. Why is it moving it? Okay, undo. I got another plan. Go back. Just keep going back. I'm gonna undo my work. That's okay. Let's just duplicate this again. Duplicate. Start here. Okay, let's try this again. So again, this was part A. Oh, undo. This was part A. Now this is going to be part B. I'm just trying to get my grid paper back. But every time I do, it gets distorted. This. Okay, I think it worked that time. All right. And then that I want to shrink down. Matter of fact, I can just delete it, to be honest. Delete. Nope. Let's try this. Yeah, it's just temperamental. This will get it done. Okay. All right, cool. So now we got our graph paper. So I'm gonna get rid of these guys again. And then that guy. Okay. And then we want the subintervals. Okay, I think we're moving and grooving this time. So then this guy, so now basically the half tick marks. So okay. So then to kind of help with that, now I'm not going to plot those points exclusively, but what I'll do is I'll go here to my table set. And instead of changing by 100, now I want my table to change by 50. And then I'll just have this table over here as a reference, but I'm not going to use it like in my drawing. Matter of fact, I'll take a screenshot and include a screenshot in the notes. We're almost done with this. But that's why I was kind of like, I kind of hesitated because I was like, it's a little bit tedious and time consuming because it's graphing. It's not too terribly bad conceptually, but where'd you go? Did you go to the previous slide? Yes, you did. Cut. And paste. Shrink you down. Again, I'm just going to use you as a reference. I'll let you chill out like over there. Okay. Okay, so now let's go ahead and do our subintervals. So our 50 subintervals, I'll start with that second one here. Oh, it's a little off. Let's go like this. I'll just do this one first. And then I'm going to do my duplications. There we go. Okay. Okay, so duplicate. So again, that first subinterval, so from 0 to 50, if we use that left endpoint, it's pretty much a flat line. Okay. Duplicate. And then this one, the height of that one is really 27,500. So, it's not going to be exact. 27, about like here. Okay. So then I think we got that one. So then I'm just going to duplicate. And I'm just doing the subintervals for 50. Okay, let's keep going. That one is 150, so that one needs to come down just a little bit. That's about there. And again, that height at when x is 150 is 67,500. So just below the 70, right? Let's keep going. I'm going to duplicate. And then like this. Okay. Then I'm going to duplicate. Right there. Duplicate. There. Okay, we're good. We still have a solid 20 minutes, give or take. Duplicate. And then it should be a repeat of the one that's on the left. Duplicate. Duplicate. And I'm basing all these on the top left corner of each rectangle. The height, I'm basing it on the top left corner. Duplicate. Okay. Okay. All right. So we should have a total of 12 subintervals. Again, based on the top left corner. These are based on the top left corner. Okay. So then the area of each rectangle. Okay, let me do this real quick. Again, I'm being a little bit extra. Okay, I can't see anything. It is writing. Let's undo, 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 and redo. Okay. So for whatever reason, I think I just clicked on the wrong one. Try again. 2, 3, 4. There we go. That's better. And then style. I want that to be thin. Oh, style. I want that to be thin. Come on, let's go. Right here today. That's good enough. Fill looks good. Okay. And then we're going to position it. Okay, duplicate. And then I'm just filling all these in. And then we'll be ready to rock and roll. Okay. Just about there. Okay. Okay. So now, with this example, again, we have the same curve, but instead of doing 6 subintervals, now we've done 12. So we've doubled the subintervals, right? To get the width of each subinterval, we said b minus a. In this case, we said b minus a divided by 12. So each width ended up being 50 units. And so then now to get the area under the curve, we add up the area of each rectangle, right? So let me suppress this. Oh, I gotta go like this. This whole process just to suppress this thing. This, and then expand it back. Boom. Okay. So now the area, change it back to this one. The area is going to be approximately, right? So that first rectangle, the area is 0 plus the width is 50, the height, so when x is 50, the height is 27,500. So we're going to say that 27,500 times 50. Okay, plus that the next height is 50,000 times 50. All right. Okay. 67,500 times 50. 80,000 times 50. 87,500 times 50. 90 times 50. I think they all repeat all the way back, all the way to the end except the 0, right? So, okay, let's just do it. So then we'll say plus, now if we just said what, the 87,500 times 50. Oh, that's not right. 500 times 50. Plus the 80 times 50. 67,500 times 50. 2 more, 50 times 50. And I think the last one is a 27,500 times 50. Okay. All right. Let me make sure we got 12. 1, 2, let me see. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay. Let's put a plus here. Okay. So then we just need to crunch the number. We could factor out the 50 like we did last time. And everything is basically times 2 except the 90. All right. Okay. I think everything is doubled except the 90. Okay. So what I'm going to do, I'm going to say 50 times, we got our 0 plus 2 times 27,500. Okay. Plus 2 times 50. 1, 2, 3. Okay. 50, 67,500. 2 times 67,500. 67, 80,000. 2 times 80. 1, 2, 3. 2 times 87,500. Plus just the 90 without the 2, because it's only one of the 90s. Hopefully I got my numbers right. We should get something close to the previous. Approximately 35 million, right? And that's close enough. So here, we got a result of 35,750,000. Right? Okay. All right. Again, a little bit. We got a solid 10 minutes, a little more than 10 minutes. So I don't really want to keep it. I usually like to leave about 5 minutes at the end. Okay. So in part A, when we did 6 subintervals, we got 35. We got 35 million. In part B, when we did 12 subintervals, we got 35,750,000. Right. So what do you think is the difference between A and B as far as these results that we're getting? Right. Which do you think is a better approximation? Part A with all those excessive gaps, or part B that's like a more high resolution kind of thing, right? We broke this into, we started with 6 subintervals. In part B, we did like 12 subintervals, right? So I think it's pretty clear that like the more subintervals we have, the better the approximation is going to be. So this in a similar fashion to the way we introduced the derivative, where we had that second point, and we got, as that second point got closer and closer to the first point, we got a better and better approximation. It's a similar thing here, where the more subintervals we take, the better our approximation will be. So then in the subsequent lectures, we're going to explore, okay, can we take it to the nth degree? Can we do nearly infinite subintervals, right? And so that's when we start to explore like, integration techniques, and what happens when we take the limit as the change goes to 0, right? So as the width of each subinterval tends to 0, we get a better and better approximation for the area under the curve, right? So again, the way we did this example was just for like to kind of provide a little context behind what the integral is showing us. And so again, in the future, we're gonna take smaller, we're gonna explore ways for those subintervals to practically go to zero, right? That's what's coming down the pipeline. If you're really curious, you want to, again, you don't have to wait on me. It's already there in the recordings, right? So let's kind of explore how the book worked those examples, right? So for part A, they divided from the closed interval from 0 to 600 into 6 intervals of size 100, right? The B minus A divided by 6 in this case was 100. Okay, so we got the same thing. And it looks like they also used the left endpoint of each rectangle, and they got a total area of 35 million the same way that we did, right? So we kind of worked, we drew the graph from scratch. We did a little bit of like, completing a square at the graph, and we got our inverted parabola. We plotted our vertex, we plotted the points, and then, we used our table to basically find the height, and we pretty much did the same thing. So then and you see the 35 million there, right? So we did all this. So then for part B, we divided that same subinterval, the same graph. Instead of 6 subintervals, we did 12 subintervals, and they each had a width of 50 units, all right? Okay, and I think they got the same image that we got, same result, 35,750,000, okay? Let's see if they go deeper. Okay, so thus the area under the curve is approximately 35,750,000. Okay. Let me see if it mentions it here. So the area under the curve can often be interpreted in a meaningful way. The units of the area are found by multiplying the units of the input variable by the units of the output variable. It's crucial that the units are consistent. Geometry can be used to find areas of regions formed by graphs of linear functions. A Riemann sum uses rectangles to approximate the area under the curve. The more rectangles, the better the approximation, right? I know I stumbled over that, but the more rectangles, the better the approximation. The definite integral, as the integral is as x goes from a to b of f of x dx, is a representation of the exact area under the graph of a continuous function, y equals f of x, where f of x is greater than or equal to 0 over a closed interval ab, right? So again, what we looked at today was just the Riemann sum. We broke it up into like finite subintervals. Next time we'll go deeper to say, okay, how do we get the exact area, right? And so that's basically what the integral is, right? The area under the curve. And we'll explore some of those techniques next time. Are there any burning questions before we go our separate ways? Any burning questions? Going once, going twice. Let me think. So yeah, we're coming down the pipeline. We're pretty much done. Once we get to the end of chapter 4, then we're just going to be reviewing in preparation for the final. So I mean, we're pretty much in the home stretch. If possible, if you're able to do this, I would encourage you to just try to go ahead and finish all of your assignments. You can use my pre-recorded lectures found on my YouTube. Like, share, and subscribe. Shameless plug. Make sure your notifications turn on at least while you're my student. Once you get the grade that you'd like and you're done with it, you can leave the subscription and just change the notifications, right? You don't lose anything and you have everything in. Sometimes I do some gaming content, but I probably should do more. I don't know. I just be in my head too much. But yeah. So again, we're going to be wrapping up chapter 4 pretty rapidly. But yeah, if possible, try to go ahead and finish, and then that way you're just waiting on exam 2 and the final. Hopefully by now you've already have something that's working for you. Either you've connected with the tutors. You can make use of my office hours. You know how to reach me. You have my office cell phone. Are there any other burning questions before we go our separate ways? One once, one twice. Okay. So then for Wednesday, again, we'll go ahead into the next section, which is going to be section 4.3. And we'll go from there. If there are any other burning questions, we're going to go ahead and end the session here. And from one beautiful mind to another. Enjoy the rest of your evening, gentlemen. And I'll see you next time. Take care. Peace. Okay. Okay.